Okay, lecture 5 will deal with graphs of different kind, how graphs are a handy tool in displaying our experimental data set. That's what we're going to talk about, okay? Hopefully you will get to do it, or if you haven't done it, the lab on graphing using Excel. Okay, so you will get to plot your experimental data using Excel. And then once you master that process, then you will use that skill continuously throughout your experiments because you will need to plot standard curve in your assay measurements. Okay, so this is a really absolutely important tool you need to master. Okay, so the basic concepts about graphs. Graph is an excellent tool to visualize the relationship between two or more variables. For example, when you do an experiment, there is something called independent variable. And based on independent variables, you'll be measuring out dependent variable outcome from your experiment, right? So the relationship between independent variable and dependent variable are two variables that are shown through your experiment. The relationship between those two will be shown up easily if we use a graph. Okay, otherwise it may be just a bunch of numbers that's hard to understand the relationship. But if you plot them on a graph form, it's easy. If there's a linear relationship, it's going to show up nicely. Okay, so you'll use most likely a two-dimensional graph that's made up with x and y values. Okay, the coordinates are the location of your data points on your graph on the two-dimensional space. And then, yes, like I said, the linear relationship between those two variables will show up, and the relationship will be described as a mathematical equation. So y equals how y values are related to the x values. That's a mathematical relationship. It's 2x. That means every one y, there's twice much x value change. That's the relationship, right? So that is a slope. In this case, number 2 is a slope. And this slope is described as the change of the y value, okay, and with the same amount of x value change. So, y2 minus y1 divided by x2 minus x1. That is the slope, okay. So that'll explain the linear relationship. And the equation, it may have something called y-intercept. Y-intercept is the y value when x value is 0. Okay, so example in this line, that is the y-intercept value. So y equals 2x plus 1. So that 1 is the y-intercept value, because when x is 0, then y equals 1. That's what y-intercept is. Okay. So display the result of an experiment, like I said, is really handy tool to use the graph, because in your experimental design, something called independent variable, that is the main control you give to your experiment, right? When you do that, the measurable outcome from your experiment is considered as a dependent variable. So if you have two different sets, okay, you can use those sets in a graph, so their relationship can be determined. In that case, normally the independent variable values, the x values, independent variables will be plotted on the x values, and then dependent variables will be plotted on the y values. Okay, that's how you normally plot. Okay, so here you go. Independent variable values are entered into x values, and then dependent variable, the measurable outcomes from your experiment, will be entered as y values, and their relationship, the coordinates, will show up on your graph. Okay, so the important function of a graph is of course showing the relationship between x and y, right? So you may have something like that. Instead of one linear set of relationship, your relationship may have different phases. For example, let's look at this red line here. Okay, if you look at the red line, what do you see? It's not just a single line that's running through the entire space. Instead, what do you see? There are three different phases: first phase, second phase, and then maybe third phase, right? So if you do that, then you cannot say there's only one relationship, one linear relationship, because that doesn't work. There may be three different linear relationships: one here, another here, and another here. Okay, so you cannot use one mathematical equation to describe x and y relationship in this case, because the relationship is changed from here to here, one relationship, from here to here, another one, from here to here, another one, right? So when you see something like that, we can point out the threshold, the points where X and Y relationship is changed. Okay, those are thresholds. Okay, so in a biological experiment, biological data, those thresholds typically appear in many cases. Think about your enzymatic assay, for example. Okay, you change the amount of substrate and change the amount of enzymes and measure the conversion of substrate into a product. Okay, so at the beginning, nothing may happen like that. Okay, because you don't have enough substrate, so enzyme may be sitting there. Okay, but all of a sudden, if you give enough substrate, the reactions start to happen. So the conversion of substrate into a product may happen rapidly. So there may be a second, relationship that may happen. And then at the end, if you give too much substrate, then what happens? Okay, not much change on the relationship, or maybe, the enzyme is used up or something like that. So there's no change. So you can see those kind of thresholds or change of the relationship typically from biological data. Okay. The application of linear graph. Where do you use your graph? Of course, in your analysis, in your assay, yeah, graph is handy. Okay, especially in your quantification. Okay, because there's something called the standard curve you need to plot in your assay. Okay, and once you have the standard curve plotted, then you can use your standard curve and its equation when you try to predict the amount of your unknown sample. Okay, when you try to quantify it. Think about your first or second experiment. Let's maybe endotoxin assay, LAL assay. So in that assay, the first thing you need to do was what? You had to do the assay sensitivity determination, right? You had a standard amount of endotoxin, serial dilution, and then you measured the gel forming point using that. That was the assay sensitivity, right? And then once you determine the assay sensitivity, then what did you do? You were able to use the assay sensitivity in your own measurement of endotoxin in different water samples, right? Because you try to see the similar trend in the gel formation point, and from that you can determine the minimum amount of endotoxin present in the the last gel forming points. So that was just as a standard curve. Okay, so you can use that. So examples are here. When you try to quantify amount of DNA, protein, okay, and then you do an experiment of gel electrophoresis. For example, try to quantify, try to estimate the size of those molecules using electrophoresis. Depends on their size, their migration distance may be different, right? So when you do that, you use something called standard samples, which you already know their sizes, and then measure their migration distance. So based on that, you can plot a standard curve. And then once you plot the standard curve, and then if you have a sample that size is unknown, then what? You run that sample on your gel and see how much you migrate. And then you plug that migration distance into your standard curve. It's going to give you that estimated size of your unknown sample. Okay, that's how you're going to use your standard curve. And how about this example? So what do you see here? This graph showed you IgG, which is antibody immunoglobulin G. Okay, standard curve. So x-axis, independent variable, what do you see? The amount of IgG. So from 0 amount all the way up to maybe 20 milligram per mil amount. Okay, there are different samples that were prepared. And then what do you see? And those samples were measured using a spectrophotometer at 450 nanometer wavelength. The observance were measured, right? You see some kind of linear relationship up to here, and the relationship changed. I guess that's the threshold. Okay, so if you have something like that, that's a standard curve. From there, you can get an equation. Okay, once you have that, then what? You're going to use that for a known sample. Let's say you have an unknown IgG sample. Okay, you want to find out how much of IgG is there. Then what do? You plug that unknown sample into into the spectrophotometer and see what its observance is. Okay, let's say the observance came out to be 0.7, which is about here. Then plug that 0.7 into the standard curve. Okay, right here, and it meets the standard curve, right? And bring that down to the concentration. Then that'll be the concentration of your unknown sample, which is about what? About 0.4 or something like that. 0.4. The 4 milligram per milliliter. So that's where you're going to use a standard curve in your sample assay. Make sense? So constructing a standard curve happens a lot in your essays, right? So you know how to plot your standard curve, of course. So series of standards containing the known amount of substances, maybe concentration of materials you are familiar with. And based using those, you're going to measure the responses of instrument using those standards. So that's what your standard curve is. In this case, what? Amount, the concentration versus the observance, just like the previous graph, okay? So if you plot the relationship, the data points, that's the standard curve. Okay, once you have that, right, then this curve will be handy when you have a sample that's concentration is unknown. Then just plug that in and measure its concentration. So whatever the observance it is. Okay. So when you have a standard curve, so if you have ideal standard curve, when you connect the dots, it's going to come up on the same line. So that's going to be the ideal standard curve. But most likely, when you plot your standard curve, they're not going to be ideal. So your data points may be everywhere. Okay, and then when you try to draw a line, single line, which can connect all the dots, that may not happen. Okay, then what do you do? So under that condition, you're going to draw something like best fit line, which will go through most of your data points as much as possible. That's a best fit line, or another name for that is trend line. Okay, so Excel can do that for you if you just select that option. Okay, you're going to draw a trend line among your standards data points. It's going to draw the line for you. Not only that, you can also estimate how close that trend line is to all your real data points. That's describe the R-scale value. And then you can also develop an equation from that trend line. So the software can normally handle that automatically. Okay. So trend line, best fit line would be really handy. For example, you got that equation y equals 3x plus 4 was the equation you got from the trend line. So that's mostly a linear relationship. Well, let's say you have some kind of curved line showing up, and when you try to get the equation came out to be this way. So y equals 2x squared plus 5x minus 8. That's what the exponential kind of relationship is showing up there. If that's the case, you have a scared equation. Okay, and that's fine. I mean, you can still use that in predicting the unknown samples. Okay, and again, the R-scale value here is correlation coefficient value. Okay, that shows how close your best fit line is to the true data points. If it is perfect, your best fit line is connecting all the dots, then R-scale value should be 1, which is 100%. Okay, but if it's not perfect, it's going to be smaller than 1. It's going to be 0.9 something or point whatever smaller value. But good best fit line should be above 0.9, above 90%. Okay. Prediction, yes. If you have some kind of standard curve, you can predict the value of unknown samples, of course. Okay. Equation and graphs are used to make predictions. Okay, so if you have a linear relationship, it's really handy. And you can also summarize the relationship between two variables, right? And then what if you have ambiguous relationship? What does that mean? If it's not linear, that's what it means. So the example is, what if you have growth of bacterial cells, how much they double within a given time? Okay, if you do that, you will have this curved line showing up because cells double every certain time and within a given time, so it's going to show up as an exponential relationship. So one example. That's fine. So it's going to be y equals 2 to the x's exponent mathematical equation is what you're going to get. Okay.